So often when we write x of t with a vector symbol above it, we're referring to this package of two functions, two unknown functions whose that we're trying to solve for when we solve a differential equation. So we're sort of packaging them together like this. And you can view this as a linear combination of the vectors 1, 0, and 0, 1, with the functions as the coefficients. So I want you to look at it like this. And the basis we're using in writing out this linear combination is the so-called standard basis, 1, 0, 0, 1. So this is often called E1, and this is often called E2. Or sometimes in physics you see this called like I hat, and this one called J hat, or whatever. So, so we're writing things out kind of like this. X vector of t is a scalar function x of t E1 plus a scalar function y of t E2. And then we're interested in solving for x of t and y of t in a differential equation like the ones we've been looking at, for example, x prime equals ax, something like that. Okay, so keep this in mind, that this is a way of writing down, this is a way of expressing that x of t is sort of one component of the full vector solution and y of t is the other component. Okay, now let's suppose that you have a differential equation like this, x prime equals ax, where A is a 2 by 2 matrix of constants. And let's suppose that you have already solved the eigenvalue problem for A, and you found two eigenvalues and two eigenvectors, linearly independent eigenvectors. So this is one of the good situations. It's not this situation that we've been avoiding talking about. So you know you're definitely in one of these many situations listed here. Okay, so I want to say that this gives us a different way of looking at the differential equation. Instead of expanding out our vector of solutions like this and focusing on the individual functions x of t and y of t, what we're getting from here, assuming that v1 and v2 are really linearly independent eigenvectors, what we're getting from solving the eigenvalue problem is a superior basis to use rather than the standard basis 1, 0 and 0, 1. So let's expand it out as something times the first eigenvector plus some function of t times the second eigenvector. Let's express our solutions like this. Instead of looking at their 1, 0 component or their x component and their 0, 1 or y component, let's look at their v1 component and their v2 component. So I need names for these functions. I certainly shouldn't use the same names, since that would definitely cause conflict. I wanted to use u and v, but I think v would conflict with the name for the vector. So how about u and w? So u of t and w of t. So this is sort of like a change of variables. Instead of focusing on solving for x of t and y of t, in the end we're focusing on solving u of t and w of t. And then if we want to, we can figure out how to rewrite things in terms of x of t and y of t. All right, well, so let's carry out the change of variables and then rewrite our differential equation using this superior basis v1, v2. So if x is this, and I want to rewrite the differential equation, then I should figure out what is x prime. So then x prime will be u prime of t. The derivative is linear, just carries through like this. v1 is a vector of constants. W prime of t. v2 is a vector of constants. Now let me write the differential equation. So I've got basically x prime, so this on the left-hand side, I just copy that, equals a times x. So this stuff. And now you can see why the eigenbasis, v1, v2, is superior to the original standard basis of 1, 0, 0, 1. I can actually multiply a through here, and it will do something useful. So a distributes, right? That's the whole linearity thing. but a v1 is lambda 1 v1. You see? So something very simple happens where if I had used this basis, I would be looking at a e1, right? A e1 isn't anything particularly useful. It's just whatever is the first column of A. A e2 is the second column of A. So I wouldn't get to do what I'm about to do, which you'll see. So here we get, I'm going to write the lambda 1 on the left side. We get lambda 1 u of t v1, right? And then here we get lambda 2, a v2 is lambda 2 v2. So I get lambda 2 wt v2. And so our differential equation, just duplicate this at each step. Our differential equation now looks like this. Now, hopefully v1 and v2 were linearly independent. So if they are, then we can match up coefficients, right? The only way for this linear combination of v1 and v2 to equal that linear combination of v1 and v2 is for this and that to be equal, and for this and that to be equal. So now we're back to the setup of having a differential equation system. U prime of t equals lambda 1 u of t. W prime of t equals lambda 2 w of t. So we're back to the original sort of problem type, right? Here we started with sort of two functions, x of t and y of t, and two differential equations. X prime of t equals something with x and y prime of t equals something with x and y. So two unknown functions, two differential equations. That's what this was. Here we are again, two unknown functions, this time u of t and w of t, and two differential equations. But look what has been achieved. These are not coupled, right? They're decoupled. This is how solving the eigenvalue problem for A has been decoupling coupled systems for us. So here, you know how to solve this one, right? The solution is, you don't need to do anything fancy with matrices. The solution is just u of t equals e to the lambda 1 t, right? That's one solution, and the general solution is any scalar multiple of this. So you could do that by separation of variables, or you might just know, you probably know off the top of your head by now, that if you want a function whose derivative is lambda 1 times itself, then e to the lambda 1 t is the thing to use. And then the solution here, e to the lambda 2 t, or any scalar multiple, if you want. And actually they should be allowed to vary independently, these scalars. So here's your two-parameter family of solutions. So what's our, if we want to go back to figuring out what is x of t in the end, what is that? Well, we had expanded it out as unknown function v1 of t, v1 plus unknown function v2, like this, and then we figured out what the unknown functions have to be, right? So we figured out that u should be this, and we figured out that w should be this. And look at that. That's what we've been doing, right? So I haven't actually shown you anything new here. I just hope I'm giving you a different perspective. This will be helpful for the next discussion. I hope I'm giving you a different perspective on what we've been doing this whole time. You see, after you solve the eigenvalue problem for A, sorry, my handwriting was just bothering me here. After you solve the eigenvalue problem for the matrix capital A, you get eigenvalues and eigenvectors, lambda 1 v1, lambda 2 v2. Then we've said, do this, create this construction, and you will have a solution to your differential equation. And this will be a linearly independent one if v1 and v2 are linearly independent, and then a linear combination of them will be your general solution. So this is just what we've been doing, and we're just looking at it in a different way. And hopefully you're seeing how the original problem, when I first brought up systems of differential equations where you have two unknown functions, the original problem was they can be coupled, and that can make it difficult to handle. That problem is resolved by solving the eigenvalue problem for A. You see that by finding these vectors such that A's action on them is simply to scale each one individually, so AV1 just popped out the scalar, AV2 just popped out the scalar, that led to a decoupled system. So instead of u prime involving u and w prime involving u and w, u prime only has u on the right side, w prime only has w here on the right side. So what has happened is we've gone from, so basically by solving the eigenvalue problem for A, we've gone from this system, so this is sort of x vector, x with a vector symbol above it prime, or x with a vector symbol above it. These are just these vectors that consist of x prime, y prime, x, y. So we've gone from this, where A might not be such a great matrix, to this. So the unknown functions are now u of t, w of t. It's kind of a change of variables. Instead of x and y, we're focusing on u and w. And it looks like this. So this is u prime, w prime, if I write this in matrix vector kind of form, equals a certain matrix times u, w. And what matrix? It's a diagonal matrix. Lambda 1, 0, 0, lambda 2, right? This is the matrix of coefficients corresponding to this system of differential equations. So decoupled system of differential equations is one where the matrix of coefficients is diagonal. That's why diagonal is so great. And that's why often solving an eigenvalue problem for a matrix is referred to as diagonalizing the matrix. So our original matrix here, I haven't been writing down names for the components, but it could be any matrix, maybe looking like A, B, C, D, who knows. So I want you to look at these two differential equations as really the same in some sense, as long as you know how to transform between the variables x, y and the variables u, w. They are the same. How do you transform, by the way, between x, y, and u, w? The relationship is this, is that u of t and w of t are the names of the v1 and v2 components of the vector x, which consists of standard basis components x of t, y of t. So all you need to know how to transform between x of t and y of t is contained sort of here in this bunch of information. It's a change of basis. You may have learned about these in Math 4a. It's basically a change of basis, and then these coefficients can be transformed to these ones, or vice versa, by focusing. There's ways of doing it. But anyway, if you keep in mind a way of transforming between the variables x and y and the variables u and w, in some sense, these are just two ways of looking at the same differential equation system. And these matrices, similarly, these matrices, this one and this one, are thought of as two ways of looking at the same matrix. So these are, they're different matrices, but they're the same, they're the same transformation. By transformation, I'm referring not to just a matrix, meaning a grid of numbers, but thinking about how the matrix acts upon vectors, how it transforms vectors to other vectors when you apply it to column vectors. These are the same transformation, but in different bases. Bases is the plural of basis. It's the same transformation, but looked through a different lens, looked at through different lenses. This one looks through the standard basis lens. You want to write vectors in their standard basis components to figure out how this transformation works, whereas this one you would have to write in an eigenbasis kind of lens. So solving the eigenvalue problem for our original matrix, this one, is a way of coming up with a good lens, a good perspective, a good basis. Good in the sense that the matrix, when looked at through that basis, is diagonal. So in the next video, I want to leverage this idea that these are the same transformation but in different bases. I want to leverage this idea to come up with another way of thinking about how you branch into the different cases here.